Mabuhay Physics, everybody. So, welcome back. It is Tuesday, October 8th. And yesterday, remember we talked about these free body diagrams. As great as your pictures might look from time to time, don't care. Right away, just not important at all. If you can draw a good free body diagram to make sense of a problem, you are going to be sitting pretty well. Okay, we sketched one free body diagram right here. And it looks like the numbers changed. Notice, remember, we always originate from the object, which is just a particle on our picture, or a dot, if you will. And then we left off yesterday combining forces, or talking about this. Now, forces have a magnitude, which is just their size, and a what? A direction, because they're vectors, right? Now, if we wanted to do like vector addition, tip to tail, we could. We could physically draw it. But maybe, just maybe, there's an easier way to think about this. So I'm going to start off today with just an automatic curveball for y'all. I want you to do the following. I want you to make a free body diagram, which we call as FBD, and find our net force, which we will make sure is very clearly written as F sub net. Okay, I'm going to give us a context, and I want you guys to see if you can't do this. So on A, short sentence, a skydiver falls, or dives rather, at constant velocity. All right, that's it. That's all you get. I want you to try to draw me the free body diagram. The forces you will not be able to label with numbers because there's no information given, right? But you can draw me a free body diagram of this and we'll make sense of it. But I'm going to give you guys about a minute. The pictures aren't going to be crazy. I want you to think about the system, that's our skydiver, and the forces that are acting on a skydiver. We're not working in our perfect idealized world right now. Like, we're working in reality. If a skydiver jumps out of a plane, what forces are acting on them? I'll give you about a minute. As we go through, I'm not going to draw a picture. What's the system? What? It's a skydiver, right? And I was going to reword it, but we don't need to. Cool. So check it out. Here's my skydiver, and notice I'm intentionally going a little bit lower than right underneath. Everybody, I think, is going to be able to identify the very first force without any issue. Right away, the force that they start experiencing pulls them downward, right? And they accelerate. What causes their acceleration? Gravity. Okay. Can we just all agree that gravity is down? This is my force F of gravity G. Now, that's not the only one, because here's where the language and our understanding and our definitions really start to matter. A force causes or might cause an object to do what? Do you remember what we said yesterday? Check back in your notes, and I can check in mine too. But I bet we have something about what the force causes somebody to do. Okay, so maybe the force is just a push or pull. But acceleration results from unbalanced forces, right? Okay, what do I tell you about this skydiver? How are they falling? The fact that they're falling at constant velocity tells us something about acceleration. If we're at a constant velocity, like we'll just use 50 meters per second, which is super fast. 50 meters per second, they just keep falling at that. Are they accelerating? So when you see this term, constant velocity, that is your like warning signal that acceleration is equal to what? 0 meters per second squared. Now, the part of this that you have to really be wary about is gravity, if acting alone, produces acceleration of almost 10 meters per second squared, right? Like 9.8. What fights gravity as a skydiver falls through or plummets towards the earth? Air resistance. If they're no longer speeding up, there must be another force to balance out so that they don't accelerate. And I'm trying my best to make this the same size. There's only one little issue that I have with this picture. And maybe it's not even an issue because we don't have values. I really want to be able to say that the force of gravity is negative. It's clear in this picture. And I'm going to let you guys help me decide. Without numbers, does it make sense to say negative Fg? Or should we just call it Fg and understand that it's a negative force? Not rhetorical. Are we cool with just keeping it FG? Okay. So, as we look at this, if they're at constant velocity, it means that if you were to take the force of your air resistance, and we'll say F of air, plus the force of gravity, this winds up being all the forces that are acting on this person, and that is just called net force. F net. Regardless of what it is, what are they going to do if we're not accelerating? Say it again. So what do you mean by keep going? So you're talking about the person, right? Okay, so that was my bad. What are those forces going to do when we add them if this person isn't accelerating? If they're not accelerating, is there unbalance or balance between those forces? There's balance, which means the net force, when you added them all together, what should it be? 0. Boom. Equals 0. And what's the label for force? It says capital N, that stands for what? Newtons. Cool. We will be using more of these, but I think it makes more sense to let us get some good numbers and stuff. Okay, we're going to go over to the computer in just a second. I'm going to walk you through what I want you to collect. You don't have to write all this down, but I do want you to record some data for me. So, when you open your little piece, we are jumping into, before we were talking about force and motion, we're going to zoom in a little bit more today. We are going to start our main topic for today, which is going to be force and acceleration. Okay, if it's in white moving forward, don't write it. Okay, what I want you guys to do is you're going to open up that PhET value, and I want you to record. You're going to play with it for a second to get used to it, and I'll pull it up so you guys can ask questions about it if you need to. I want you to choose a mass, and record acceleration for 5 different forces. Okay, as we look at this, we're going to make sure we have a few things. So if you guys want to pop over to the PhET thing, underneath you guys probably see that you have the option of net force, motion, friction, and acceleration. I want you to choose the acceleration option. Your screen should look like this. You get this cool guy and a refrigerator and a box and other people. Everybody have this on your screen. Okay. First thing I'm going to tell you is I want you to take this friction. Let's just get it out of there. We're going to go all the way to none. Notice it makes it icy, which isn't quite true, but it's close. Okay. I'm going to let you guys play around with this for a couple minutes just to see if you can't figure out what the buttons do. We'll meet back up. Cool. Play around with it. See what you can get this guy to do. You can drag different objects over here just by dragging and dropping. And then I will tell you this pause button is going to be super duper useful soon. But I'm going to give you a couple minutes to play around with it. So I've put these 3 random objects. There is one thing that's a huge pain. If I do this, like I'm trying to push her and I'm pushing her, she's moving, I can see the applied force. The second I let go though, it goes back to 0. Now, is this gal ever going to stop? Why? There's literally no friction. There's nothing to slow her down. So this gal, she'll just keep going forever and ever and ever and ever and ever. Okay, as we go through it, here's what I want you to do. Pick some combination of objects, and then we need a couple things up here. We need to see the mass. So I'm going to click this mass box. Okay, and then if you want to see the sum of forces, we can, but there's nothing crazy going on with it. I'm going to show acceleration, and I want values because it's going to show me in meters per second squared. Now, it can be super hard to try to measure this, right? Like, if I want to know, and I'm just going to pick something. Somebody, let's see, I have 130, 170. I have 170 kilograms here. When you click this box that says masses, it'll show you. Now, I had to add them up, but, okay. So check it out. If I'm using this, I don't want you to use this number. I just want to demonstrate how this is going to work. When you record your data, here's what I want it to look like. And I'm just going to erase this since you guys already have it or you've started going. We need 5 values. The mass needs to be included on this. So for mine, I know that for this first sample, the mass was, and we'll just make a table here. So mass, we need force, and we need acceleration. And I always put my units up top when I'm making a table so that I don't have to, bless you, so that I don't have to write it down on everything because that gets, bless you, kind of be a pain. So I'm going to show you guys my first little 5 table real quick, and we'll just check at it. Now, all of mine are using 140 kilograms. All right, so here we go. I have 140 kilograms right here, and I want to see the acceleration at a given force. There's a couple ways we can do this. If I start going forward, like I'm at 42 newtons, if I hold it here, can you see my acceleration? Okay, it's 0.25, right? Now, here's what I'm going to suggest. I'm going to pick nicer numbers, and we'll see. I would encourage you guys to find a mass that ends in 0 eventually. Okay, I'm going to stop her real quick. But if you are struggling to get this, we can pause it. Notice, not accelerating anymore. If you pause this, pause, you can actually adjust this. Instead of sliding, if it's paused, it'll stay. So if I want to get this measurement, check it out. I can go to 70 newtons, for example, and I'm just going to hit play. And it didn't do it. Why didn't, oh, I didn't hit play. Okay, at 70, my acceleration was 0.41 meters per second squared. Cool. 70 newtons, 0.41. Cool. If I want to change this without it sliding back immediately, I can pick another random number, 107, and let's hit play. At 107, my acceleration is 0.63. I'm going to do this 5 times. Once you do this 5 times, I'm going to let you guys help me decide. Are you graphing it by hand, or are we going to use like Google Sheets? Do you know how to graph on Google Sheets? All right, we about to learn then. So, as you're recording data, what I want you to do is go ahead and open up your Google Drive. If you're on your Gmail anywhere, you just click the waffle here and you can open up your drive, or just click a Sheets. And I will try to make this the right size to fit in here, but it always tries to drag itself to fill the whole screen when I do it. Okay, I'm going to start a new sheet. And then I'm going to do exactly what I just did on that table. We have mass up here in kilograms. We are going to have, lost my train of thought, force in newtons, and we are also going to have acceleration in meters per second squared. Okay. Oop, go over. Now, a couple formatting things that just, I don't use Google Sheets normally. If this, like I notice this doesn't fit up here because it's too long. If you highlight here where you see that double bar and you double click, it'll fit it to your data. Cool. So I have 140 kilograms and I'm going to have 5 values. So once I have 140, we can just slide right down and we get all of them filled in at 140. Cool. Collect your 5 data points with different forces and different accelerations, and I'll bounce back and forth between these. I actually had a couple values. 70 is 0.41 for me. Okay. 70. Goodness gracious, I'm all over the place. Okay, 70 newtons, 0.41 meters per second squared. (107 newtons is 0.63. And I won't talk out loud. I want you guys to get your 5 values for your random mass with no friction, okay? Cool. I'll give you a moment. So there's a couple ways you can do it. So one, if we hit play, like you'll see that we can just drag it. You should be able to drag it. Or alternatively, if you just want nice values, check it out. I can just apply 50. Now we need to turn friction down because we don't want any friction. So what I do, because he's going to start going faster and faster, I'll just pause it. You now have a data point 50 and 0.2. Make sure you turn your friction down there, man. Make sure you turn your friction down.
It just was down. It's weird.
Yeah, if you hit reset, it'll reset everything.
Yeah.
Cool. Now, I would use the pause button because if you try to go back and forth, it's not going to take long with no friction to get to 40 meters per second, and that person's just going to fall down. You're not going to be able to apply any more force. So if I just pause it, I can get all these big values that won't be like too expanded. So here's my last one. 455, 2.68. Then I'm going to record a bunch of our data, and we'll just do like two or three of them on the board. When you get 5 done, will you let me know, and I'll just read out, or I'll record what you have as well? Oh, question, Nick? Okay. Good call, Thompson. Make sure you get your, oh, you are, cool. 240. And then, are you struggling to make sense of how to get this?
No,
Okay.
just doing it slow.
Okay, no, you're good. If you pause it, so notice you won't accelerate anymore. What I would do is, if you want to, you'll have to reset it, which means you'll have to click your boxes again and move your friction. Can I pick your value? So Schwarman says acceleration. We don't need speed yet. And then values if you want. Yeah, values. Okay, so hit pause. You have 50. Go ahead and keep it there. Just hit this above 50. Hit start. And pause it. Okay, so check it out. Record that one. And then I want you to do it again for 100 or 50, 250. What was your max? Will you do me one more set of 5? Okay, will you do me a set of 5 with 100 kilograms? And then when you do it, I would move it over. You don't have to necessarily. But I want you to use 50, 100, 150, 200, 250 newtons. Okay, Fern, you got a data set?
Yeah.
What's your mass?
170.
170. Okay, I'm gonna drag this down here just to make sure we have it. And then this is gonna be weird, but can you just give me your forces in order so that I can just go straight down?
50, 100, 200, 300, 400.
Okay, and the corresponding accelerations.
0.29, 0.1, 0.59, 1.18, 1.76, 2.35.
Cool. All right, and I made somebody do a second data set here because these ones are going to be easy. If nobody's done it yet, if you already have your data set, help me get one more to verify. Do 100 kilograms with 50, 100, 150, 200, and 250 newtons. Oops. And I made Mickey do this one, 50, 100, 150, 200, 250. And Mickey, once you have all those values, if you would read them to me, that'd be cool. I have a feeling I know what they're going to be. I bet it's 1, 2, 3, 4. Whoa, 1, 2, 1, 2.5. Is that right? No, that's right. 3, 4, and 5. Okay. And then I'll have one more person here in a second. You'll hook it up with the hundreds. Whoa. So I have way more data than you guys, and that's okay, I hope. Were you guys able to get the hundreds done yet? Well, Will you do that for me? We do a mass of 100 kilograms, no friction. You have hundreds?
Yeah.
Or the 50s?
It was the 4 kilograms?
Yep.
Oh, I did
You did hundreds?
Yeah.
Is this going to be right? Is it 0.5, 1, 1.5, 2, and 2.5? Cool. All right. So we have a ton of data here, and this is all my data that I just collected with the exception of one of Fern's. What we're going to do is we're going to look at something. We're going to construct a graph. Now, I know that the mass is just set here, but you guys probably don't have a ton of experience with this. I prefer Excel, just so you guys know. Google Sheets is like Excel with a lot of the capabilities removed. It's still going to be worth our time. So once you have a data table in front of you, I want your ears. We're going to go step by step. You're not going to wait until I get 3 steps further to tell me that you missed something. Tell me right away if we struggle, okay? Step 1. We are going to create a graph where I want to see the relationship between force and acceleration. That's my whole goal as we're looking at it. So all I need to do, notice, I'm not going to select the labels. That's just here, and there's a reason I don't put letters and labels and stuff in here or units. I'm going to click here. I'm going to highlight just this data set. One table is all I'm highlighting. All right, looks like everybody has this highlighted, I think. Okay, I'm going to go to Insert. It's still highlighted, I can see it. And I'm going to insert a chart. Okay, it is going to open up this graph underneath, and we're going to be able to see it. Okay, does everybody have a graph that says acceleration versus force? Yep, so that's okay. Yours might look like this if you go in first. Okay, regardless, you should see acceleration versus force. Yay or nay? Okay, now, over on the right, we get our chart editor. I'm going to hit this chart type, and I'm going to go to scatter plot. So I'll scroll down until I find it. Looks like scatter. Now, beyond this, there's all sorts of stuff. Did yours come out labeled correctly? Cool, that's a good sign. All right, I'm going to come around and check just to see, because we'll verify. Oh. So let's see, on this one, let's see, we have force versus acceleration. Okay, so yours came out backward, right? So that's okay, and I'm trying to see why yours would come out backward. It might instantly leave the table. Oh, you went. Interesting, are you sure? With a force of 100 newtons, -2. So I'm going to have you, I'm going to hook you up with some nice ones, okay? So let me see here, I'm going to think this out. I think so as well. You might be able to do this. Okay, so let's go all the way back. I'm going to ask you to do a favor here, and I'm just going to cheat with you, okay? Okay, so let me think this out. We're going to use 100 because that's easier. Actually, we'll use 50. Because I know what this is going to look like. But you could verify and you could collect all this data. I don't know what happened here. Oh, there it's right again. Well, let's just undo that then, because I don't know why it changed. It wasn't negative before. Okay, that's all right. Check out. We'll do this, and I'm going to insert our chart. Insert chart. And we'll see. So that's force. Now it's correct. I think that you must have highlighted from here up, and I didn't realize that would matter. Okay, so I'm okay with this. All right. Now we all have a graph that looks kind of like this at this point. See? Okay. Now, before we do anything else, can you guys see, is there a relationship? As force increases, what does acceleration do? As I go bigger forces, so that's positive in the x direction, what do the y values of my accelerations do? Do they increase seemingly in a proportional fashion? Or if we use pre-calc language, does it appear that this looks like force or acceleration varies directly as force? This looks like direct variation to me. Now, as we go through, there's a couple other things that we can do. If you have this open and here's our graph, and you click Customize, So I've chosen this tab. It was on setup, and I've moved it over to customize. If we look through here, I don't know why they use this language, but we have the option of series. This is our y-axis. If I roll down, a couple things I can do. I can add a trend line. And then all of a sudden, I see that, oh my gosh, they fit perfectly. That's pretty cool. So there is a relationship here that obviously they do work together. One more little piece of data that I want to look at is if we go a little bit lower. So I clicked trend line and it gave me all this stuff. If I say, hey, I want the label and show me this equation, we get this mess. Now, this graph is going to be ugly, and that's okay, but I want to notice something here. First, these numbers suck. When you see E negative 0.3x, what is that telling me? We saw it on our calculators before. E shows up on the calculator means what? It's scientific notation. So this would be times 10 to the negative 3 is all that would be. Okay, when we look at it, this might not be crazy meaningful yet, but I want us to look. Did you guys all get data that shows up in a straight line just like this? Okay, this one's going to be hard to pick out. You get something different? Okay, so if we go over here, if we, so let me look here. I'm going to double click on see if we get more options. Okay, so I'll tell you yours is a straight line. I don't know why this doesn't like it, because it should be letting us, and it's just that it's a weird thing on your tablet. That's okay. Okay. All right. As we look at it, is a connection, like, you can see a connection, I imagine, but is it super clear? Maybe. Like, it's clearly directly related, but here's what I want us to do. When we look at this, if I asked for the slope at any given point, could you tell me what it is? Like, probably not, right? Like, I mean, I know it's this, it's 0.00589, because I see the equation, but other than that, I don't get a 10 out of it. Here's what I want us to do, though. I want us to graph a little bit by hand. It's nice to see here, and I'll graph them up here as well. But I want to see something work out, and I'm going to go back to the notes for just a moment. As we look at this, we get a nice straight line. Even if you can't get the line to show up on your page, there exists a single line that runs through all those points. What I want us to notice is that as we graph these, we see, I hope, a connection. What I think I notice is that when we get a linear model like this, we get direct variation. And very specifically, we know that acceleration, and we can use one of two words. We can, from pre-calc, and not everybody's in pre-calc, but this is direct variation. We can either say acceleration varies directly, or acceleration is directly proportional to the force. Which would you prefer? You like proportional? Okay. Acceleration is directly proportional. Proportional. There we go. To the force. Now, beyond this, and this is a little bit of a pre-calc throwback, what this immediately means, if we wanted to model this, is that A is equal to K, some number, times, what is it varying directly as? So careful, acceleration varies directly as force. Now, we have this direct variation formula, and we are on the precipice, I don't know this word. Do you guys know the word I'm trying to say? I think precipice, but that sounds odd as I say it. Anyway, in this context, the big question that remains is I can see there's a relationship, but I want to find this value. What is this? And it turns out that once we get it, we're going to make sense of it. So here's what I want us to do. I'm going to give you some free data, and we're going to try to figure out what this K value is. As I go through, I want you in your notes to make a single graph, but I'm going to give you 3 sets of data. So check it out. We're going to have our graph that we're going to make, and I would make it kind of to scale. Doesn't have to be perfect, but we are going to have force, F, in newtons along the x-axis, and we're going to have acceleration in meters per second squared on our y-axis. Okay. Here's our data tables that I'm going to hook you up with. I'm going to give you 3 tables, and I'm going to use a different color for each. I know that not everybody has that capability, but I'm going to do our first table for 50 kilograms. And I know that this is going to work super duper nicely. I'm going to have force as my x, and I'll have y as acceleration. Okay, I'm also going to do this with 100 kilograms, where we'll have force and acceleration. And I'll hook you up with these numbers, or I can make you find them. I probably should have just made you find them in hindsight. That'll be a change for next year. And then next one, do you want 150 or 200 for the mass? 150, okay. We'll do force and acceleration. Okay, turns out that you could verify this on that simulation as well. Do you want to find the numbers, or do you want me to tell you the numbers? Okay, that's fine. All right, so check it out. With 50 kilograms, we're going to get the same values every time. I'm going to check what happens with 50 newtons, 100 newtons, 150, 200, and 250. Now, when you plug in these values, and feel free again to verify, we're going to see nice accelerations. I have 1 at 50, 2 here, 3, 4, and 5. Super easy. Okay, at this point, notice, I'm just going to jump up and I'll say, check it out, here is on my axis. I'm going to use these same values, so I'm just going to put them on there, 50 newtons. And then that would be 100, this would be 150, 200, and 250. And I'm going equally spaced. How high up on the axis should my scale go for the data that we've collected here? On the y-axis. What's the largest acceleration you see? 5, right? So this is going to be weird, and I'm just going to try to eyeball it out as best I can. I'm going to say here's 2.5, and here's 5. Now, there's a really cool thing that winds up happening because of this direct variation. To draw a line, you really only need how many points? 2. Now, I didn't include it, but I bet you guys can reason it out. If I open that simulation and I said, hey, I'm going to apply a force of 0 newtons, what's it going to spit out at me? 0 acceleration. So there's a point for free. I'm going to put that point right at the origin. 0, 0. That makes sense. You don't apply force, you don't accelerate. Now to get my straight line, I only need one more point. And I think on mine specifically, 255 is like the easiest point I can choose. If I connect these lines, literally every single one of these points is going to hit. Here's 51 and 150, or sorry, 102. 150 is at 2.5, and so forth and so on. Are you guys cool with just using the 2 points instead of, like, I just put all 5 on so I could see them? Okay, I'm going to give you the data, and I want you on the same graph to plot these other ones. And we're going to think about the slope here in a minute. So at 100, when we apply 50, and I'm just going to skip some if that's okay with you. I'm going to give us a little bit different data. 0 and 0 still going to happen. And I'm just going to give us 250 this time, or we'll do 100. That's okay. If I only show 0 and 100, we still get 2 lines, and we're going to wind up with 1 there. On the orange, we'll still get 0, 0, because that's always going to make sense. But this time, I'm going to switch, and I'm going to give you 300. And let me think this out here real quick. Uh, 302. Okay, I want you to plot these other 2, and I'm going to make sure that we can see it. I'm going to label mass equals 50 kilograms. I'll give you a second. I want you to get the green and orange. They don't have to be different colors on yours, but get all 3 graphs up here. Probably.
Yeah.
Yep. I think there's straight edges in your desk if you want to use them. You need one? I have boxes and boxes and boxes here. When I taught math years ago, every year I'd use the heck out of these, and inevitably I'd go through like 300 or 400 a year because people would lose them and they'd break and whatnot. So one year I just bit the bullet and bought like 5,000 of them, and I'm never going to run out. If you ever need a straight edge, Miss Osmond has thousands of them in her room. Anybody need a new one? Yes. Oops, sorry. And let's see, 302. Wow, that's a hard one to get. I don't even have the point 300, but that's okay. Yeah, that's probably close. This line, keep it going. Like, those are the points. All right. Now, as we look at this graph, I don't think we're going to see anything like super duper crazy with it. But tell me if this logically makes sense. We're applying, and I can check at each point, like at this point 50. This is 50 newtons applied to 3 different masses, right? Does it make sense that the heavier the object, the less it accelerates? Like applying the same force, if I try to push something that's 50 kilograms, it's not going to go near as slow as 100 kilograms. Okay, as we go through here, here's my challenge, and I'm going to let each group do this differently, which we're split up weird. You three, I want you to find me the slope at any point on the yellow line. Okay, you three, I want you to find me the slope at any point on the green line. And you four, I want you to find me the slope at any point on the orange line. If you need to get other data, I don't mind if you go over to PhET and change it, but I want you to find me the slopes. Because if we look back at our model, y equals kx or y equals mx, I'm just trying to avoid m because of mass. This is just the slope, right? I think, but I want to figure out what it is. So I'll give you guys a second. I want you to find me the slopes. Yellow, green, orange. Talk it out. You guys are all lone wolfing today, which is fine. But I want the slopes. And notice I'm going to say k equals so we don't confuse it with mass. All right. So, need another minute or you guys have slopes? Not rhetorical. Do you guys have a slope? Do you guys have a slope? Do you guys have a slope? Okay, because you're struggling or because it just takes a little while? All right, well, let's get down to it. Real quickly, to check out the slope, you only need 2 points, and I don't really care which ones you use. I only gave you 2 points over here. Let's see. This is x and this is y, right? Cool. So change in y over change in x. If I do 2 minus 1, I get 1. And if I do 100 minus 50, I get 50. Do you agree that this slope is 1 over 50? Everybody cool with that? Okay. For green, if I change 1 minus 0 is 1, and 100 minus 0 is 100, the slope is now 1/100th. Is that what you guys came up with? Okay, for the last one, if we go 2 minus 0 for a change in y, I get 2. Over 300 minus 0 is 300. I get 2 over 300. Does that simplify? To 1 over what? 1 over 150. Okay. You may or may not see the significance of this statement yet. I did, thank you. I'm going to sneak out one step ahead of you guys. I'm going to write in blue. I want you guys to have this. I want you to take this, and with your nearest neighbors, let's check and see if we can't find it. For mass equal m, k is equal to something. There's a very clear connection here that you may or may not have noticed before we did this. The mass is certainly connected to these, I think. So notice the force always goes up by 50 because I'm using that. Like I'm picking that value so that this will work out. If it's 50 kilograms, what was the slope? What about 100 kilograms? And now you see it, right? Do you see the pattern yet? So check it out. Are you so we're trying to collect a lot of data and that's muddling it a little bit. But we got our slopes out of it. I'm just checking the change in acceleration over the change in the force. And this is to all three of you if you haven't seen the pattern yet. For 50 kilograms. And this is for everybody rather. For 50 kilograms, what was the slope? 1 over 50. Okay. For 100 kilograms, what was the slope? 1 over 100. And for 150 kilograms, the slope was 1 over. For a mass of m, what do you think the slope is going to be? 1 over m, right? It's just 1 over the mass. So what we're connecting here is we've just found this value for k, and we're about to connect it with Newton. It's just 1 over the mass. Do you guys agree that that is what we see very clearly presented? Maybe it wasn't obvious at first, but this is a huge takeaway. With this, we are about to give Isaac Newton a handshake or a head nod or whatever random thing you want to associate it with. The connection that we just made, all of a sudden, is we've made this super important observation. I know at this point in time that acceleration is exactly equal to kf, that's where we started, where k, what did we just find it was? 1 over the mass. And I'm going to use 1 over m for mass since that's what we're looking at. Okay, very specifically, this takes us then to being able to say that acceleration is 1 over the mass times the force. Is everybody on board with this? I'm just plugging in. Okay, at this point, we get our last rearrangement. Acceleration then is equal to force divided by mass. And I like to take one more step here because nobody loves fractions. Could I just say then that force is equal to what times acceleration? Mass times acceleration. Okay, Newton's proud of us. We'll jump in here tomorrow. Does this look familiar to anybody? Okay, if not, Miss Holloway's going to have some very angry words for you guys. All right, see you cool cats and kittens tomorrow. There's no homework tonight, unfortunately. There will be tomorrow. Oh, man, we're so close to finishing this up.